Okay, it's time to get started. Before I get into chemistry today, there are a few announcements. So periodically, I will have announcements for things not related to this class. So if you're a member of a student organization and you want me to advertise your group, feel free to send me stuff. So the first one is there's a couple of pre-health organizations that are having their first meetings of the semester, and they're trying to obviously recruit new members all the time. So the Pre-Dental Association is meeting next Thursday, the 24th, 6 p.m. This is all in the notes, so if you don't remember what I say, it'll be online in Blackboard when you download the completed notes. The Pre-Dental Association, and then there's AMSA, American Medical Student Association. There's supposed to be someone from this organization here to talk. Are they here? All right, so they ditched us, but they do have a meeting Tuesday of next week. So whether you want to be a dentist or a doctor, those organizations are meeting next week if that's your career goal. They both have meetings in the evening. And then finally, the last one that's in here, which I'm not going to talk a lot about, probably a little bit early for you guys to think about the MCAT, but if you are pre-medical, you'll have to take that someday. And there's now currently a free MCAT workshop at UH that a couple of students started, one of them who took this class with me a few years ago. And they go over problem solving and test taking strategies and all that stuff. So if you want to get an early start on preparation for that, that is also totally free. All right, we will get in though now to the chemistry part. So can I make this bigger? Yeah. All right, let's try this. All right. And today we're going to talk about atomic theory. We're going to get into that very quickly after a couple of loose ends to clean up from last time. So last time we started talking about some of the early origins of chemistry and some of the fundamental physical laws, the natural laws that were come up with and discovered as people started rigorously interrogating chemical compounds and elements and things like that. And so we talked about two of those mass laws. These are all laws that revolve around masses of substances. And the first one we talked about was conservation of mass, which is that matter is neither created nor destroyed in a chemical reaction. And that's probably the simplest to understand. We've probably all seen that before or heard it before. And then the other one we talked about at the end of last time was law of definite composition, which deals with a single chemical compound. And for that compound, it's going to be made up of two or more different elements. And those elements are going to occur in fixed mass ratios that are, for that specific compound anyway, going to be the same no matter how much of that compound you have, no matter where you get it from, and all that stuff. Now, there actually is one other reminder I want to give you before I forget, because I almost did. There won't be any office hours on Friday, so just be aware of that. What? Oh, geez. I'm still on the Zoom key, so that's not what I wanted to do. One of these days I'll learn how to use a computer. Not today. All right. So let's see if I can write now. No, I still can't write. I'm going to do that. There we go. All right, anyway, no office hours on Friday. In case you were planning to come see me that day, I won't be there at all. Oh, so you guys are the AMSA people? Okay, so we're going to take a quick time out. And it's still not clear how much of that was true, but anyway, there is a meeting Tuesday. I think that part at least is a fact. All right, getting back into what I was starting to get into. So no office hours on Friday. It's been pretty light this week anyway, but I won't be there at all this week. There shouldn't be very many cancellations, but just a couple more maybe throughout the whole semester. All right, let's get back into the chemistry. So we talked about the two mass laws last time. We're going to finish with the third one that we're introducing today, which is the law of multiple proportions. This one is the hardest to probably wrap your head around. I'll admit that much, but we'll try to break it down as simply as possible. So kind of the textbook definition of this, or at least the way that I like to define it, is that if you have 1 gram of element A, so with law of multiple proportions, as the name suggests, we're talking about two different compounds now. So element A, some generic element, can combine with another element X, so these are just two random elements. And they can form, in some cases, two different compounds. So let's say this is the situation we're playing out here. Two elements combining to form two different compounds. And we should be familiar with this possibility happening. For example, carbon monoxide and carbon dioxide both just have carbon and oxygen in it, but different ratios. So when you have two elements combining to form two different compounds, the difference is the ratio of the two elements that are present in that compound. So element A is going to combine with element X to form two different compounds. It's going to combine with different amounts of X to form each of the two compounds. It's because the ratios of A and X have to be different in those compounds for them to be distinct. And so then the masses of X that combine with A, so again we're talking about 1 gram of A combining with X to form the two different compounds. Those two masses are small whole number ratios of each other. For example, when we mean small whole number ratios, we mean things like 2 to 1, 3 to 1, 3 to 2, etc. So very simple ratios. So we're going to give some real examples here in a second, but if that, let's say 1 gram of A combines with 2 grams of X to form one compound, the other compound is not going to have something like 2.37 grams of X. It's going to have something like 3 grams of X or 4 grams of X, some simple multiple of that original amount. So the dead giveaway for law of multiple proportions as you guys start doing homework problems on this is we're always talking about two different compounds. So if the problem is set up as ratios of elements in two different compounds, that should be a dead giveaway that we're talking about the law of multiple proportions. So let's see how this plays out in a real example now with two compounds of iron and oxygen. So the one on the left is a black powder called ferrous oxide. The one on the right is rust, which you've probably all seen before. These both just have iron and oxygen, but because they're two different compounds, they're going to have two different mass percents, and we see that here for the two. So ferrous oxide is 77.73% iron, 22.27% oxygen. Rust is less than 70% and about 70-30. So slightly different ratios of the two elements by mass in these two different compounds. Now let's see if the law of multiple proportions is fulfilled here. So to illustrate that this is in fact true, as I stated on the last slide more generically. So what we have to do is figure out how much of one element combines with 1 gram of the other. So really the way we do this is we take the ratio of the two mass percents. So if we're looking at the first compound, which is ferrous oxide, if we take the ratio of the two masses, mass of oxygen divided by mass of iron, or we could do it the other way. There's no reason we have to do it this way. This is just an illustration. So basically, if I take in the ratio of the two masses, we're saying what mass of oxygen combines with 1 gram of iron. We're normalizing to the amount of iron that's in the sample and saying, so if we divide the two, we just use the mass percents as the mass of each element. And so we have 27 grams of oxygen for every 77.73 grams of iron, which means, we'll just skip that for now, the ratio of the two is 0.2865. So that means if you have 1 gram of iron, you would need 0.2865 grams of oxygen to make ferrous oxide. So we're just normalizing the mass ratios per amount of iron in this case. And then for rust, we do the same thing. We see the mass ratios are different. And we'll do it the exact same way. Oxygen over iron. We could have done it iron over oxygen, and we would have gotten the same outcome at the end. So in this case, there's 30.06 grams of oxygen per 69.94 grams of iron. We're just reading off this table here, the mass percents. And when we divide those, we get 0.4329. So this is the amount of oxygen that would combine with 1 gram of iron to make rust. So different amounts because they're two different compounds. And then what the law of multiple proportions tells us is that these two numbers, the amount of oxygen that combines with 1 gram of iron to make the two different compounds, these two numbers should be simple ratios of each other. So let's verify that that's true. So we take the two and we divide them in either direction. Obviously, it doesn't matter which one goes on top and bottom. Let's just make it a number greater than 1 so we don't deal with fractions, although we will anyway. And when we divide those two, we get 1.500, which, as we should recognize, is 3 over 2, a very simple whole number ratio. So this is just one demonstration of how the law of multiple proportions works. Two different compounds, and it's basically a ratio of ratios. You take mass ratios for both of them, divide the two ratios, and those should be related to each other by very simple multipliers, not some complex relationship between them. All right, so as I said, that's the hardest one to understand, and you'll see some examples in the homework of how it's applied, but really, as I said, the dead giveaway is law of multiple proportions deals with two different compounds that have then two different mass ratios of elements. Two different compounds with the same elements that make them up specifically. All right, so let's review then the three mass laws that we've covered, because these are going to form then the basis for the theory that we're going to describe that explains these three mass laws. So we talked about last time law of conservation of mass. And again, the simplest way to think about this is that mass is neither created nor destroyed in a chemical reaction. So the amount of stuff you put in is the same as the amount of stuff you get out, even if it changes its form and changes to different compounds and things of that sort. It's always the same mass. Law of definite composition we introduced last time, which is that each chemical substance, and specifically chemical compound, we should say, we're talking about compounds in this case, has a specific proportion of elements by mass. And then the law of multiple proportions that we just finished up kind of takes the law of definite composition and expands on it and says, well, what if we have two different compounds that are made up of the same elements? How do those relate to each other? And so what this says is, again, it's kind of wordy and hard to put into really simple terms, but if two elements combine to form multiple compounds, which is a very common situation, it's not rare at all. So we said, carbon and oxygen, iron and oxygen was the example I gave. Lots of examples where the same 2 to 3 or however many elements can combine in different ways to form many different compounds. Each compound will have a different mass ratio for the two elements. Now this is not 100% true. There's some complex examples we might see later on that are called isomers, which are two compounds that have the same formula but different structures. So that's not 100% true, but in general, each compound is going to have a unique mass ratio, especially in the early days when they were doing these on really simple systems. This was largely true for them. But anyway, each compound will have a distinct mass ratio for the two elements, and that's what makes them different from each other, is the elements combine in different ratios. And then this is where it gets a little bit funny, is when we take the ratio of those two ratios. So it's a ratio of ratios, which sounds weird to say it, but that's what you're really doing here. The ratio of these two ratios is a small whole number or simple fraction. So as we saw, if one element combines with, 1 gram of one element combines with some amount of another element to make a compound, it can't just combine with any random amount of that other element to make a new compound. It has to be some simple relationship between the amounts that combine. So those are the three mass laws, and then these kind of came out, and as we talked about last time, when you have a law, which is a set of observations or a collection of laws, as we do here, which are a set of repeatable, consistent observations that have been made, hundreds and thousands of times, then you want to explain those laws. Why did this happen? Why is this true? And it's a theory that's going to be what is used to explain those. And the theory that explains these three laws is called Dalton's atomic theory. And so, as we said, the idea of atoms had floated around a little bit even in ancient Greek times, but it was really Dalton's atomic theory that put it all together and really helped explain those three laws at a very microscopic level. So the essence of this atomic theory, as the name suggests, is that substances are composed of tiny particles called atoms. And his theory includes the caveat that these cannot be decomposed further. Now this is also not 100% true, as you'll learn in chemistry too, when you talk about nuclear chemistry and the ability to, decompose an atom further. But if you do that, you're going to change the identity of the element. So really, you can't decompose an atom any further without completely changing what it is. So atoms are the simplest building block. You can think of them as like the Legos of matter. The littlest blocks that you can pull out of a piece of matter are these atoms. And then another one, which, again, not exclusively true, but for just talking about chemical reactions is definitely true. Atoms cannot be converted into different atoms. So if you're doing nuclear reactions, which you won't learn about until the end of chemistry 2, this breaks down a little bit, but for the stuff we'll talk about in the first semester of chemistry, this is 100% true. When you're doing a chemical reaction, you cannot convert one atom into a different atom. You can't change the identity of that atom in any way. In other words, elements cannot be interconverted. So we know that elements are substances that are made up of one type of atom, and so if you have, let's say, carbon taking part in one of your reactions, you're not going to change that carbon into oxygen. You have to put oxygen in to use oxygen as part of that reaction. All right. So atoms cannot be converted into different types of atoms. They can't be interconverted with each other. All right. So then the third postulate of this atomic theory is that what makes different elements, what makes atoms what makes elements different from each other? Why is carbon and oxygen different? What distinguishes them from one another? And his theory, this part of the theory is that atoms of a given element have the same mass and other properties that are identical. And these are distinct from all other elements. All right, again, we'll see even later today that this one is not 100% true. This is actually the one that's probably the most false of all of these, but it still was a good starting point, saying that, well, if you have different elements, what makes them different from each other is that the atoms that compose those elements have some distinctions between them, the mass being different or other things. So we'll get in more detail about that later today. And then finally, the last one deals with the formation of chemical compounds. So we know that forming chemical compounds involves combining elements in different ratios, and taking it down to the atomic level, then chemical compounds are formed when atoms of different elements combine in a specific ratio. And that chemical reactions really just involve reorganization of atoms. So again, you're not creating or destroying atoms in a chemical reaction, you're just reorganizing them, changing what they're partnered with, changing, as we'll see later on, how they're bonded with each other and all these different things. But really, you're not creating or destroying new atoms. And this last one here kind of explains the law of definite composition and multiple proportions, because we can't have fractions of atoms. So if you had, let's say, carbon and oxygen, and you want to make compounds from those, you can combine, let's say, one carbon with one oxygen atom. That would make one compound. But you can't combine one carbon atom with 1.3 oxygen atoms. You have to combine it with either 2 or 3 or some whole number of others. So basically, because atoms can't be broken down into smaller pieces, everything combines in these relative whole number ratios, and then at a macroscopic level, that translates to the masses of them that combine, which also are related to each other by whole number ratios. So really, because atoms can't be decomposed further, and because they combine in specific whole number ratios when forming compounds, that then relates to a lot of the mass laws that we talked about, specifically the definite composition and multiple proportions ones. So this is kind of the unifying theory, saying that, you know, atoms exist. They're the simplest building blocks of all substances, and that's why when we study the masses of things that react with each other in chemical reactions, this is why we get those types of outcomes that we see in the three mass laws. So that's the theory. And then the last thing we want to talk about in chapter 1, this is kind of placed in a weird spot, but I just want to go over it quickly because it is in there and it's still helpful to think about. Dalton's theory doesn't really address some of the finer details of, well, how do we know what ratio the atoms combine with? So, you know, they've been measuring mass ratios for a long time. We talked about the mass ratio of carbon dioxide last time and how it's, 32 grams of oxygen and 12 grams of carbon, and people have been measuring those things for a while. But then how do they get to the knowledge of, well, what are the ratios of the atoms? How do we know that carbon dioxide is 1 carbon and 2 oxygens and not, because we can't measure individual atoms, we can't see them, we can't weigh them out or anything like that. So how do we know that that's the specific ratio of atoms in that compound? And that was come about by studying gas phase reactions. It's a little bit harder to do on other types of reactions because when you're using solid substances that you have to measure out by mass, the relationships between mass and number of atoms are not so simple, as we'll learn later on. They're different for every substance. But when you're talking about gas phase reactions, the relationship between volume and number of atoms is a very simple one, as we'll see here. So this is kind of just a quick primer of how do we actually determine what these chemical formulas are, going from the knowledge of just mass laws that we started with previously. So there was a French chemist, Guy Lussac. I'm sure you can tell he's French by his name. And his observation was that if you have gases at equal temperatures and pressures, and again, these are things we'll touch on in more detail when we talk about gas laws, so just to give, we're again not going to be too worried about this at this point, but if you're doing reactions of gases, and those gases are all at the same temperature and pressure, meaning that they're under the same conditions, when you combine them in chemical reactions, they combine in whole number ratios. So fixed whole number ratios. So as an example, let's say at very high temperature it will be high temperature because there's going to be an explosion involved in this process, but let's say we combine hydrogen and oxygen. You probably have seen videos of hydrogen balloons. I'm not brave enough to do them in class, but hydrogen and oxygen can combine to form water. And what Guy Lussac observed is that anytime you do this reaction, you have exactly 2 volumes of hydrogen that combine with exactly 1 volume of oxygen. So volume being whatever volume unit you're using, liters probably being the most common in this class. So if you had 2 liters of hydrogen and you want to react it with oxygen, it will react with exactly 1 liter of oxygen. Or 1 liter of oxygen would react with 2 liters of hydrogen. And those would then form 2 volume equivalents of water vapor. So both the amounts of the gases that react with each other in terms of volume and the amount of gas product that's formed all have these really simple whole number ratios, and they're fixed every time you do that chemical reaction. Even if you change the amounts, the ratios of the volumes will always be the same. So this was his observation. And it wasn't until later on that Avogadro, whose name you've likely heard before, had sort of an interpretation for this. And we will talk about Avogadro's law and more implications of this in a lot of detail in chapter 6, I believe it is. But his interpretation was, well, if we have gases at the same temperature and pressure, and we have equal volumes of any gas in the world, so equal volumes of any different gas, doesn't matter what gas we're talking about, have the same number, and I'm going to use the word particles here, I mean either atoms or molecules, depending on what the smallest building block of that substance is. So in other words, if we have one volume, if you have 1 liter of hydrogen and 1 liter of oxygen, they have the exact same number of molecules in them. It doesn't matter that they're two different substances. In a gas, specifically, there's a direct relationship between volume and number of atoms. And that's what Avogadro kind of came up with as an explanation for this. And so then what that means is that Guy-Lussac's observations can be scaled down to the atomic level to say, well, if this is what's true at the macroscopic level, if 2 volumes of hydrogen combine with 1 volume of oxygen, that also means 2 atoms of hydrogen combine with 1 atom of oxygen. So you can really interpret this also at the atomic level, and they will form. There's a complication here that I'll get into a little bit later, but anyway, the point is that they combine in a 2-to-1 ratio also at the atomic level, meaning that water has the familiar formula H2O, 2 hydrogens, 1 oxygen, because the same is true at the atomic level as it is at the macroscopic level. So let's just do a quick pictorial representation of these then, where we can again think about both the macroscopic and the microscopic. So the one we just talked about, hydrogen and oxygen, what Guy-Lussac observed was that if you have this box here that's representing some volume of hydrogen, he found that two volumes of hydrogen will react with 1 volume of oxygen to form 2 volumes of water. Now the complication here that is not something we need to worry about, but is why the ratios that I wrote on the last slide are not exactly the same, is that most gaseous elements are diatomic, meaning they're not made of hydrogen atoms and oxygen atoms. They're made of H2 and O2. We'll learn that later on. But essentially what this means is that your 2 volumes of hydrogen are going to have, at an atomic ratio, 2 molecules of H2, and then that's going to combine with 1 volume of oxygen, which would have half as many oxygen molecules. So there's 2 hydrogen molecules, and then there's going to be 1, that the ratio is going to be 2-to-1 still at the atomic level, and then those combine to form H2O, which has one oxygen and 2 hydrogens. Maybe I should color code these a little bit better so you can see that. And so that's how they sort of figured out then that when you mix 2 volumes of gas together, that also then gives you the ratio of the atoms that are combining with each other at the microscopic level. So that's how they determined then the formula of water was H2O, because they noticed that it's always reacting in a 2-to-1 ratio, which then is directly related to how many atoms are combining. But then there's other gases that are different, so this isn't always necessarily going to be a 2-to-1 ratio. So if you take hydrogen, and let's say you take 1 volume of hydrogen in this case, whether it be 1 liter, 1 gallon, whatever your favorite unit is. If you combine hydrogen with chlorine, how do I get a different color? Guess I only have 2 color choices here. There we go. Alright, so let's say we take 1 volume of hydrogen, and if we react it with chlorine instead, which is another element, this time it only will react with 1 volume of chlorine. So hydrogen does not react in a 1-to-2 ratio with chlorine, actually in a 1-to-1 ratio. And what that means is then that the molecules that form as the product with hydrogen and chlorine in them now have hydrogen and chlorine in a 1-to-1 ratio instead of 1-to-2. So it just, again, relates the microscopic to the macroscopic properties and shows us the ability then to determine chemical formulas. So by studying these gas phase reactions, because gases have this very special relationship between volume and number of atoms or molecules that are present, you can study these gas phase reactions and you can determine chemical formulas. This was the first way it was done. Now, for many other types of substances that aren't gases, you have to do a lot more complicated analysis, and that's some things we'll learn about in future chapters of this course. But at the outset, really, the first examples of people being able to determine chemical formulas was, Guy Lussac and Avogadro kind of putting their heads together and figuring out that these gas phase reactions have that correlation between macroscopic and microscopic. So that takes us to the end of chapter 1. Before I move on, is there anything else you want me to review or clarify on the stuff that we've already covered? Yeah? So, number 4, as far as I know, is very true. It's number 3 that we're going to talk about today is having some parts that aren't quite right. So, point number 3 assumes that atoms of a given element all have the same mass, and that's not necessarily going to be true, as we'll see. Okay, so there is something about those atoms that's identical for each element, but it's not necessarily the mass. Okay, so it's number 3 that we're going to talk about today. That's really the only one you have to worry about is not being rigorously true. There's some, as I said, for number 1 and number 2, there's some nuclear chemistry weird stuff that comes into play that makes those not exclusively correct in those settings, and you'll touch on that at the very end of chemistry 2. We're going to not see it at all in here, but for number 3, we're going to talk about a little bit later today how there's something about this that's just not quite right. Okay. Anything else? Yeah.
Is the law of multiple proportions? Does it matter which proportion on top?
No. So this was just when I did this example here, I was just randomly choosing to put oxygen on top, iron on bottom. We could have flipped the ratio. You would have just gotten the inverses of these numbers, and when you divide those two numbers, they would still come out to 3 to 2 or 2 to 3, depending on how you divided them with each other. Yes. We're not going to probably do a lot of numerical problems for multiple proportions, but it's mostly going to be like concepts and understanding what it means and which situations illustrate it. Okay. Anything else quickly before we move on? All right. So we're on, I think, to chapter 2 now. Technically, I don't keep close track of the textbook myself, but maybe this is still chapter 1. I don't know. I don't read the book anymore. I'm a bad student. All right. So you guys should though. So we're going to move on now to talk about the structure of the atom. So we've established that substances are all made up of atoms, these little building blocks that make up everything. But, are they just, little spheres, little tiny marbles that make everything up, or do they have more to them than that? And obviously, as you probably already know, there's more to it than just a marble, basically. So there's what are called subatomic particles, which are the components that make up atoms, and the components that make different atoms different from each other, as we'll see. So the first person to kind of get after this a little bit was J.J. Thomson. This is the name of this fellow here. And he did what's now famously referred to as the cathode ray experiment. So there's a small picture of it up here. It might be hard to see from your seats, but hopefully in the printed notes it'll be obvious. And I think there's probably diagrams in your book too if you have that. So essentially what he did here was that it's not too different than a light bulb, but a little bit different setup, where you have, at one end you have an anode and a cathode. So basically these are electrodes where you're applying a really high voltage. So you just, supercharge, I don't know what voltage you use, but it's usually pretty high if you're going to generate a cathode ray. And what he found is that off of the cathode, which is one of the electrodes, you had a beam coming off of it. So there's this beam of something coming off of the cathode when you supercharge something with a really high voltage. And so what he found is he called these things cathode rays because they come off of the cathode. And he discovered that the cathode rays are repelled by the negative pole of an electric field. I don't remember exactly what year he did this, but we should kind of keep in our minds that a lot of this atomic theory stuff that we're talking about, structure, atomic structure particularly, that we're getting into now, this is all relatively recent history, like early 20th century, which maybe doesn't sound too recent to you guys, but in the course of human history is a pretty recent thing. So a lot of stuff had been worked out about chemistry and about physics and electric fields and stuff like that. But he noticed that when you generate these cathode rays by applying a really high voltage, they are repelled by the negative pole in an electric field. And a pretty simple concept that we should all be familiar with is that like charges repel each other. So if it's being repelled by the negative pole, that means the cathode ray is also negatively charged. And he called these were eventually called electrons. I think he had a different name for it, but we're not going to worry about that. But eventually they became known as electrons. And another key observation is that they could be produced from many different materials. So the cathode doesn't just have to be some specific material to get this to work. You can get cathode rays from a lot of different things. So it's not just copper that works or just iron that works. It's really, typically the cathodes that work well are metals, but at any rate, a lot of different materials produce these cathode rays. So it's a pretty general observation. It's not just specific to one type of material or another. So the conclusion from this then was that all atoms must have electrons. So electrons are one of the key constituent components of an atom. So that's kind of what came out of this by studying many different materials, finding that they all had these negatively charged particles coming off of them. They must be present in all of those substances. And the other thing he determined that was sort of semi-quantitative was the charge to mass ratio of the electron. So his experiments weren't sophisticated enough to determine the exact charge of the electron or the exact mass of the electron, but it could determine the ratio of those two. Basically, it's all physics, but it's determined by how much the cathode ray bends as a function of the electric field that you apply. So if you've taken physics, that might make a little bit more sense to you. But he could determine at least that ratio for the electron, but not the absolute values for each of those. But this is credited as being the discovery of the electron, the first set of experiments that showed us that these electrons are present in everything. So knowing that there's electrons present, and following up on this then, this guy Millikan did an oil drop experiment. Now this sounds like it actually on paper is like a less sophisticated experiment, but it's actually even more complex and very difficult to do on your own. People have repeated it, and it takes a pretty high level knowledge to do this. Isn't something you could easily cook up in your basement if that's the type of thing you'd like to do on the weekend. But here's what he did. So he had these. He basically did what's called atomization of oil. So he made these really tiny oil droplets, and then I think he shot them with X-rays or something, some high powerful radiation that he hit these oil droplets with, so that they acquired a negative charge. So the whole point is, he generated negatively charged oil droplets. There's a lot of physics that go into this, where he determined the radius of those oil droplets, and then you can calculate the drag force as they fall, and from that you can calculate the mass of the oil and the gravitational force. All these physics things that go into determining this. But essentially, the point of his experiment was that he allowed these oil drops to fall. Gravity will take them down eventually. So he generates them up here. They fall through this chamber. And if you don't have any sort of electric field present, they're going to just fall freely and reach some terminal velocity that's determined by their size and their, the drag force and all those physics things. But these falling negatively charged oil drops, what he did was at the very bottom, he set up an electric field, and he cranked up that electric field to figure out how strong of an electric field do I need to stop these drops from falling. All right, and again, the negatively charged plate for your electric field is here at the bottom, so that's pushing up on the drops as gravity is pulling them down, and at some level, those two forces are going to balance each other, and the oil drops are going to just kind of hang out there in midair. And if you turn up the electric field strong enough, they're going to start rising. And based on, again, mathematics that we're not going to get into, based on the strength of the electric field, the size of the oil drops, and all that stuff, you can back out what is the charge on each of those oil drops. And what he found was that the oil drops don't all have the same charge. They're not all the same as each other, so some oil drops fall faster than others in the presence of an electric field, meaning they have different amounts of charge attached to them. But the ratios of those charges were all whole numbers. So it was all some whole number multiple of the smallest fundamental unit of charge. So let's just use simple numbers here. If one of the oil droplets had a charge of 1, there would be oil droplets in there that have charges of 2, 3, 4, 5, and so on, but there wouldn't be oil droplets that have charges of 1.17 and 2.37 or any random number like that. So all the charges on the oil drops were, again, small whole number multiples of each other. It's not a continuous value that he observed, but discrete values for charge for all the oil drops. So you can measure the charge on each oil drop using this experiment, and they always occur in regular whole number ratios of some smallest value. And what he determined was that the charge of an electron, and I think we'll see this constant later on, or at least you will if you take chemistry too, is around 1.6 times 10 to the minus 19 coulombs. So coulombs is the fundamental unit of charge. If you read the review chapter, that should be in there. So that's what he found was the charge of the electron, and his value was actually pretty accurate. It was within like 0.6% of the accepted values today. So even as long ago as he did this, and is not terribly sophisticated as his apparatus was, he got a pretty accurate value. And again, what he also found was that each oil drop, the smallest charge that a drop would have would be 1.6 times 10 to the negative 19, and then the rest of the oil drops would have charges that are some multiple of that, 2 times 1.6 times 10 to the minus 19, or 3 times that, but not any sort of random fractional multiple of that. So that's the charge he determined, and he also determined the mass of the electron as well, so this experiment gives you both. So that's the value for the charge. We're not going to have you be responsible for that just now, but that's what he found out. That was his key contribution. He doesn't look very happy about that, but it was a very big contribution. And also since then, he did this experiment many times himself. And there are scientists out there that are much more intense than I am, and they've done like hundreds of thousands of these oil drop experiments over the years. And I don't think they've ever found a fractionally charged oil drop. So this has stood the test of time and the test of repetition, that no matter how many times you do this experiment, your oil drops are going to have some charge that's a whole number multiple of this number here. Never going to have fractional multiples of that. So that then tells you that electrons are discrete particles. You don't have continuous charge units in an atom, but you have rather discrete particles called electrons that provide the charge for the atom. And you can have some whole number amount of those. You can have 1 electron, 2 electrons, 3 electrons, 4 electrons, and so on, but you can't have fractional numbers of electrons. You can't break it up into a smaller piece than that. All right, so that's kind of the 2 experiments that led to the discovery of the electron and the realization of some of their properties. And then this led to the first proposal for what the atom looks like. And this was done by Thomson, who, again, discovered the electron. So he reasoned that if all these atoms have negative charges in them, they also have to have positive charges, because in total atoms are charge neutral, so you have to have positive charges to balance the negative charges. And his initial thought was that the positive charge was just sort of loosely spread around in the atom. It was just sort of an amorphous, sort of loosely held positive charge, and the electrons kind of float around in that. That was his initial hypothesis. So remember that hypothesis is a proposed explanation for something. He discovered that there's electrons, he reasoned there must be protons, and his proposal, his hypothesis, was that there's this sort of plum pudding model where the two are kind of just floating around inside of each other. So to put this into words then, the plum pudding model that he came up with is that atoms consist of electrons that are held in place. So the electrons aren't flying all over the place, they are bound in the atom, and that is still true today, that's not wrong. But they're held in place in this proposal by a diffuse cloud of positive charge. And that the electrons are just randomly embedded in this positive charge. All right, and this is a picture at the bottom of actual plum pudding. This, I think, is a UK thing, so I wouldn't call that pudding myself. But it's essentially a cake that has like raisins or plums in it, and the plum pudding model says that the positive charge is the cake and the raisins are the electrons that are just kind of randomly floating around inside of there. That's why it got that name. But this is the first proposal for the structure of an atom, and as I'll show you right now, that was wrong. But that's not a bad thing. Remember, this is how the scientific method works. So Thomson had a hypothesis for the structure of an atom, and Rutherford, who did the gold foil experiment, had an experiment designed to test that hypothesis. So he said, well, that's a good hypothesis. Let's test it out. Let's come up with an experiment to test this. So this was, again, Ernest Rutherford is the name of the scientist that designed this experiment to test out the plum pudding hypothesis. I guess it's Rutherford. I'm bad at spelling. My spelling is almost as bad as my handwriting. All right, so Ernest Rutherford is the name of the scientist that did this. So again, the hypothesis was that you had this plum pudding, and he designed an experiment where he took really high energy particles called alpha particles. They're positively charged and they're high energy, and he shot them at a very thin piece of gold foil, which is not one atom thick, but obviously just super thin, so there's not very many atoms for this particle to go through before it gets to the other side. And if the plum pudding model was correct, because the positive charge was so diffuse, these high energy positively charged things would just blast right through it, because they're going to be repelled by the positive charge. There's not going to be like there's not going to be like a real center of mass for them to bounce off of. They're just going it's kind of like throwing a bowling ball at a piece of tissue paper. It's just going to go right through, right? So that was kind of the hypothesis if the plum pudding model was correct. So the expected outcome was that these highly energetic alpha particles would mostly pass through. Or maybe they would be slightly deflected, because as I said, there is repulsion between the positive charges that are in the alpha particles and the positive charges that are in the atom somewhere. So maybe there'd be some slight deflections, but largely you just expect these alpha particles to blast right through. Now, the actual outcome was not too different than that at first glance. Most of the particles did go straight through. But the surprising outcome was that some of them were deflected and often at very large angles. Or some of them just reflected completely. They came straight back at the source. So that's what this shows down here. This red beam is the alpha particles. Most of them go straight through, but some of them were deflected pretty steeply or came even straight back towards where they originated from. And that was not expected with the plum pudding model. So really the only explanation for this is that the positive charge in an atom and most of its mass also I'll say most of the atomic mass, so to be clear that we're talking about atoms here. Those are going to be in a very small, dense area called the nucleus. And so it eventually got the name nucleus to describe that very dense region where all the positive charge in the atom resides. And so then this is the picture down here that's a more accurate representation of an atom than the plum pudding model. So at the center, and this is probably still exaggerating the size of the nucleus. And the nucleus is absolutely tiny compared to the size of the atom itself. So you have the nucleus at the very center, very tiny, and then you have this diffuse electron cloud that kind of, in some sense, orbits around it. We're going to talk about that in more detail also in this course. But The key basics here is that your nucleus is this really tiny, dense center of positive charge that's at the center of your atom, and that's what this gold foil experiment showed us. Another way of thinking about the outcome of this experiment is that atoms are mostly empty space. So the plum pudding model would have assumed that the mass of an atom was distributed evenly throughout the whole thing, but what this shows us is that no, the mass is actually concentrated into a very small area. You have the electrons that are occupying that area, but they're tiny in mass and in size compared to the size of the atom itself, and so really most of the atom at any given time is just empty space. And that's kind of the outcome of this experiment. So these were some of the key experiments, some of the key discoveries that led us to come up with the idea that atoms are made up of these subatomic particles. They have electrons and they have protons, and then there's one other where we're not going to really talk about the discovery of those in details, but we're going to talk about it here. So here we're going to summarize all of the subatomic particles that make up atoms. So you have protons, neutrons, and electrons. So these two, the protons and the neutrons, are both in the nucleus. The discovery of the neutron was much later on. It actually took a lot longer to realize that those were there, and that's more of a pure particle physics discovery, so not something that we can easily talk about in this course. But they did discover later on that there were also neutrons, so it's not just protons and electrons. And these all have different properties from each other. So the charge is, I think, the easiest one to comprehend. +1 relative charge for a proton. Neutron has no charge, and the electron, so neutron has a 0 charge, and the electron has a -1 charge. And this reminds me of the time I was in a bar, and I don't go to bars often, but a neutron walked in, and he came up to the bar and he said, "So how much are your draft beers?" And the bartender said, "For you, no charge." So that's a good way to remember that one. And then proton and electron, as it shows here, they are equal but opposite in charge. So the magnitude of the charge on those is identical to each other. So you only need one proton to balance out one electron. Their magnitude of the charges is identical. And then the absolute unit, as I said, is the coulomb, and the oil drop experiment got this pretty accurate. So it's 1.6 times 10 to the minus 19 positive for the proton, and it's negative 1.6 times 10 to the minus 19 coulombs for the electron. That, again, Rutherford Millikan's oil drop experiment got those numbers pretty darn close. And then the neutron, no matter what unit you put it in, is 0 charge, okay? So those are the absolute charges. Again, you don't have to necessarily memorize those numbers, but that does give you the idea of how small these particles are as well, how small each unit of charge is. That's a really tiny number on the scale of, our macroscopic existence. And then the relative masses is also important to think about. This is going to come up a lot in stuff we talk about. So the gold foil experiment said that all of the mass, or just about all of the mass for the atom, was in the nucleus, the vast majority of it, and this kind of demonstrates that point. So protons have a relative mass of 1. We call this the AMU, the atomic mass unit. Protons and neutrons are not exactly the same, but they're really close to each other. You have to go to, I think at least 4 or 5 significant digits before they start even differing a little bit. So they're 99.999% the same. Same mass, that is, different charges, of course. So the mass of the proton and the neutron are the same, and the electrons are about 2,000 times smaller than that. So the relative mass of an electron is 0.000549. So in a typical atom, greater than 99.9% of the mass is in the nucleus. Even probably greater than that in most cases, because the neutrons obviously contributed as well. So the mass of the electron is tiny compared to protons and neutrons, and then if we want to put those into absolute scales of grams, these are the proton and the neutron each weigh about 1.67 times 10 to the minus 24 grams. Now keep in mind, a gram is like, I don't know, if you took like salt and you just put like a little pile in the middle of your hand, that's probably a gram or so. So to get, you'd have to have a huge amount of protons and neutrons to even weigh 1 gram. So again, that's just, I hope, emphasizing how tiny these things are. And then the electron, as we said, is over 1,000 times smaller than that. About 1,800 times smaller if you want to be more precise. All right, so that's the differences between the subatomic particles, protons, neutrons, and electrons that make up all of the atoms. All right, so then with that in mind, we can start now talking about what are the differences between different types of atoms. What distinguishes one element from another. And the key distinguishing feature that says one element is different than the other is really just the number of protons in the nucleus. So if you know how many protons an atom has, you immediately know what element that atom belongs to. Okay, that's the key distinguishing feature between elements is number of protons in the nucleus. And then from there we can write out what are called atomic symbols. And so they look like this. They have some letter symbol that I'll just call X generically here. They have a subscript that I'm going to abbreviate as Z. And they have a superscript abbreviated as A. So we'll define what all these mean right now. So the symbol here, X, it's a 1 or 2 letter abbreviation that tells you what element you're talking about. And in case you have to type these in Blackboard and we're cruel and make these things case sensitive, you always want to capitalize the first letter. Alright, so the first letter is capitalized for any atomic symbol, 1 or 2 letters. Alright, and then what we have here at the subscript is Z. And that's what we call the atomic number. So that's going to go on the bottom of the symbol. And that simply tells you that key parameter, the number of protons in the nucleus. I'm going to use P plus to abbreviate proton. I think I had that in the last slide, but in case you're not familiar, P plus for protons. And that's given by Z. And then finally the last one here, A, which is going to be written as a superscript, is what we call the mass number. And this is the sum of the number of protons plus the number of neutrons, which I'll abbreviate as N with a little 0, neutrons and no charge. Alright, so the mass number is the sum of those two. So that's the anatomy of an atomic symbol. That's what they look like in their full glory. They have a symbol that tells you what element it is, and then 2 numbers that distinguish 2 features of the nucleus, how many protons, and then how many protons plus neutrons. Alright? And then this leads us to another important definition, which is isotopes. So we said that the number of protons in the nucleus distinguishes what element you're talking about, and that's true, but there are the situations where you have atoms of the same element. Let's say the same element to make it more clear. So these are isotopes, are atoms of the same element that differ with respect to the number of neutrons. And because they have different numbers of neutrons, they also have different mass numbers, because mass number is protons plus neutrons. So they have the same number of protons because they're the same element, but different numbers of neutrons, so then they have different mass numbers because of that. And this is the one, as I alluded to earlier, that shows us that Dalton was at least partially incorrect with his atomic theory. Because Dalton assumed that all atoms of a given element have the exact same mass. This is not true in situations where you have isotopes, where you can have 2 atoms of the same element, but they have different masses because they have different numbers of neutrons. Okay? Now, the properties of isotopes are generally very similar to each other. So you can have 2 different isotopes of the same element, and except for the mass, they're not usually that different from each other in terms of the chemical reactions they do or other physical properties like melting point, boiling point, whatever you want to characterize for those. So really just the mass of them is what's different from each other. So properties of isotopes for a given element. Are nearly identical. I don't want to say exactly identical, but they're nearly identical. And this is especially true as you get to heavier and heavier elements where one neutron is not going to make a huge difference in the mass overall. So if you have an element that has, let's go down to like the last row of the periodic table. If you have an element that has a mass number of 192 or whatever, which is what my favorite element has, if you have that and you make an isotope of that has one more neutron that has a mass of 193, those aren't all that different from each other. But for some of the lighter elements, the mass differences are more significant, and then some of the properties are different as well because of that. But in general, the isotopes have very similar properties to each other as long as the element is the same. So the simplest examples of isotopes would be there's 3 isotopes of hydrogen, and at least in 2 of them occur naturally. So another thing that's going to seem kind of random now, and will be for probably most of your life unless you really study nuclear chemistry in great detail, is that some elements have just one single isotope that occurs on Earth. Some elements have many, many isotopes, and there's really not an easy way to predict that. But hydrogen, which is the smallest atom that we have, it's going to have 3 possible isotopes, 2 of which occur naturally. So the most abundant one is just, we call it hydrogen, and it has this atomic symbol. So it has just 2 ones in the for again, the atomic number and the mass number. So this bottom number here tells us that we have 1 proton. The mass number is also 1 here. Where am I used to have a pointer here. I guess I don't have it anymore. Otherwise I had to open this every time. That one? That one? No. There we go. Alright, sorry, I wanted to get that pointer because I'm going to start pointing at things and you guys are going to have no idea what I'm doing. Alright, so here's the atomic number and mass number. If the mass number is 1 and there's 1 proton in the nucleus, that means there must be 0 neutrons. Because, again, this number here at the top is the sum of protons and neutrons. 1 proton, 0 neutrons. The next isotope of hydrogen, again, this number will always be 1 for hydrogen because no matter what isotope of hydrogen you're talking about, it will have exactly 1 proton. But the second isotope now has a mass number of 2. So the number up there is what changes for isotopes, the mass number being different for them. So this will still have 1 proton, but it also now has 1 neutron in the nucleus. So again, the difference between these two being just the number of neutrons, this one has 1 of each now. And this is what we call, sometimes it's referred to as deuterium, but it's still just another form of hydrogen. And then the last one, which is actually very important for a lot of biological studies, is radioactive. It can be generated unnaturally in most cases. Still has 1 proton because it's hydrogen, and it has a mass number of 3. So this has 1 proton and 2 neutrons, because if the mass number is 3, the sum of protons and neutrons must be 3. Alright, so those are examples of isotopes of hydrogen where the same number of protons, roughly the same chemical properties, but different numbers of neutrons that distinguishes them. So let's just do a couple problems dealing with these atomic symbols. Can I minimize this? Alright, so let's do a couple problems dealing with atomic symbols. I lost my notes somewhere. Here we go. Alright, so let's look at palladium. Just that's what this symbol PD means. You don't have to know that off the top of your head. And so again, atomic symbol is given with the 2-letter abbreviation and then the 2 numbers. So we want to know the number of protons, electrons, and neutrons in these 2 isotopes of palladium. So the number of protons is very easy to find. It's just this bottom number here if that's given. So that's going to be 46. Now to find the number of neutrons, we know that the mass, this is Z, if you want to use the same abbreviations. This number here is A, and that's going to be equal to the number of protons plus the number of neutrons. So if we want to solve for how many neutrons there are, if we take 106 and subtract the number of protons, which is 46, so this is just simple algebra to get this number, it's 60. I'll circle the answers so you can find them easier. Okay, so those are number of protons, number of neutrons. The sum of these two, 60 plus 46, has to equal that mass number there, which is 106. And then in a neutral atom, something we haven't explicitly mentioned yet, but this atom has no charge. It's charge neutral, and that means the number of electrons has to be equal to the number of protons. Remember that, and we'll use E minus to abbreviate electrons. Those two have to be the same if you don't have any net charge. Which that will also be 46. So for a neutral atom, you have the same number of protons and electrons. Because protons and electrons have equal and opposite charges, they have to balance each other. So let's quickly do this next one. Also another isotope of palladium. It's the same element, still uncharged. So that means it has the same number of protons. We don't even have to look at that very closely. And also the same number of electrons because the charge is still 0. So both of those will still be 46. When you change to a different isotope, you don't change the number of protons in the nucleus. And if you don't change the charge, as we'll get into more in a second here, you're not going to change the number of electrons either. The only thing different here is going to be the number of neutrons, as is true for any isotope. This time we have a mass number of 108. We subtract the number of protons from that. So this is the mass number, this is the number of protons, and then the difference gives us the number of neutrons, which in this case is 62. So the only difference between these two isotopes, as is always going to be the case, is the number of neutrons in the nucleus being 60 versus 62. So again, that's another common type of homework question, to just look at different ways of analyzing these atomic symbols and abstracting out the different numbers of subatomic particles. One more that we'll do is, let's say we have a fictitious element, so there is no element with the symbol Q, but let's imagine there is. And if it has 34 protons and 43 neutrons, write the proper atomic symbol. All right. So again, this just asks us to decompose, to use these numbers to formulate the atomic symbol. In this case, before we were giving you the atomic symbol, so just working backwards. So again, the generic form of an atomic symbol is the letter symbol, and then two numbers Z and A. Z is the bottom number, which is the number of protons, and we're telling you here that it's 34. And then the mass number A is protons plus neutrons, which is 34, plus the number of neutrons is 43, which is 77. So our final symbol is going to have the letter Q in the middle. That's the symbol for the element that we gave you, which was, again, made up. A goes on the bottom. Z goes on the bottom, A goes on top. So it'll be 34 on the bottom, 77 on the top. And that gives you the symbol for this element. Okay? So I think that's pretty straightforward, but again, you'll want to practice that a lot to get the hang of it. The last little wrinkle we'll throw at you now is, how do we write symbols for ions, or how does that affect the number of subatomic particles? Because there are going to be a lot of things we talk about in this course where you have ions involved. So these are charged species, either positively or negatively charged. And keep in mind that for neutral atoms that we've been talking about up until now, they have equal numbers of protons and electrons. And that's to balance the charge and make everything completely charge neutral. So what happens when we form ions, though? These are charged particles that don't have equal numbers of protons and or electrons. Now, all we're ever going to do when we're forming an ion, whether it be a positive or negative ion for a specific element, is we're going to either remove or add electrons. And this is, maybe more philosophical than you guys care about at this point, but we're talking a lot about the nucleus now. It's still an important concept to introduce at the beginning of a chemistry course, but really the essence of chemistry is electrons. So it's the electrons that are always going to be moving back and forth between atoms and chemical reactions, or that are going to be adding or subtracting from an atom to make an ion. So really it's the electrons that do all the chemistry. The protons and the nucleus kind of just are there. They determine what element you're talking about, but they don't really change during any sort of chemical process. So when we form an ion, we only remove or add electrons. And to emphasize the point clearer, we never add or remove protons when we're forming ions. And I hope it's obvious why, because if we did this, this would change the identity of the atom altogether. If you have different numbers of protons, you no longer have the same element. And another thing that's hopefully fairly clear, but I'll write it out just to have it here, is that if your ion has negative charges, you need to add extra electrons to the atom. So you add 1 electron for each negative charge, and we subtract 1 electron for each positive charge. So ions, by definition, will not have equal numbers of protons and electrons. They're either going to have extra electrons if they're negatively charged, or they're going to have not enough electrons if they're positively charged, and that's how you determine what the charge is by how many electrons get added or subtracted. Alright, so let's do a couple examples. The first one here, IR, with, this is the atomic number, mass number. You will see this element is called iridium. It's my favorite one, as I referred to before. I'll bring that up many times and see if you remember it. There won't be any bonus questions on that, but it is my favorite. And anyway, so the question is the same as we had before. How many protons, neutrons, and electrons? In this case, we're talking about ions, not neutral atoms. So the number of protons is still given by the atomic number, which doesn't change when you form ions. So even though it's positively charged, it still has the same number of protons as it would as a neutral atom. So it's going to be 77. We want to know the number of neutrons, and again, that comes from the mass number. So the sum of the two is 192. The fact that it's an ion does not influence the mass number. That's all stuff in the nucleus. We don't change the nucleus when we form ions. And so that means the number of neutrons then is the mass number minus the number of protons, which is 115. So this nucleus has 115 neutrons to go along with the 77 protons. Now when we're finding the number of electrons, this is where things are a little bit different for ions. So our nucleus has 77 protons, but in total we have a 3 plus charge. So whenever you have a net charge indicated, it's going to be here in the top right of the atomic symbol. That tells you what the charge of that is. In this case, plus 3, or 3 plus as it's often written. So if it's 3 plus charge, that means you have 3 fewer electrons than protons. You have 3 extra protons, another way of thinking about that. So that means you'd have 74 electrons. So to form the 3 plus ion, you remove 3 electrons, and now you're down to 74 instead of the 77 that you would normally have in the neutral atom. So again, forming ions, we're just adding and subtracting electrons. I'm getting a little bit low on time here, so try this one on your own. I'll put the answer in the notes before I post them, if I remember, but let's just move on to the next one so we don't have to belabor that point, because that's pretty simple. Alright, another thing I want to bring up now, we haven't talked a lot about the periodic table yet, but you are all aware of its existence, and you will be using it a lot in this course. The periodic table is another way of helping you determine how many protons something has. If you know what the atomic symbol is, you know what element you're talking about, you can find it on the periodic table, and that will tell you the number of protons in the nucleus. So on our periodic table, it's formatted this way. There are some slight variations if you look at other ones that are out there. But this whole number here, it's always a whole number for the number of protons, obviously. That one that's above the atomic symbol on our periodic table is the atomic number. So if we give you the symbol for the element, you can just find it on the periodic table, and that will tell you the atomic number directly. This number down here, in case you're curious, is related to mass number, but we'll cover it later, so you don't have to worry about it for now. So don't worry about that. It's not going to usually be a whole number either, which might sound weird at this point. But some things that come out of this then is that the atomic number, which we called Z, is usually left out of atomic symbols. So complete atomic symbols will have it. And that goes on the bottom of the left, as we said already. But very often Z is not given to us in the atomic symbol. And that's because if you know what the atomic symbol is, let's say C for carbon, you know from the periodic table that it has 6 protons, and writing out the 6 for the atomic number is kind of redundant in that case. So even though the full atomic symbol for the most abundant isotope of carbon would be this, atomic number of 6, mass number of 12, most often you're going to see them written as just 12C. You're going to leave out the little 6 because the fact that it's carbon, the fact that it has this atomic symbol, tells us that it has 6 protons, and carbon will always have 6 protons no matter what, so it's kind of redundant to keep it in there all the time. So this is the more common way of writing these atomic symbols, because the atomic number Z is redundant if you have the abbreviation or the symbol for the element. Alright, so you don't often see that Z put in there explicitly, but you'll see them both ways in your homework assignments, so you want to be familiar with its existence. Alright, one last page, if you can hang with me for just like 3 more minutes. I know we're getting anxious to get out of here, but chemistry can't wait. That's not true, but anyway, let's just finish this off. So, some sample problems a little bit more advanced in this case, just to make sure we can drive home our understanding of these topics. So determine which 2+ ion has the same number of electrons as Br-. Now for this we do need to go to the periodic table so we can see how that works here. So here's our periodic table. I wish we had one in the room, but I think the one we have in the room is covered by the screen, so that's not very convenient. Anyway, we find Br on the periodic table. There it is, and there's the number above that, which is 35. So that tells us that bromine has 35 protons in the nucleus. So that's going to be part of our question here. So we're looking for which 2+ ion has the same number of electrons as Br-. We need to figure out how many electrons Br- has. So we know that it has 35 protons because there's number 35 above it in the periodic table. If it has a 1- charge, that means it has 1 extra electron, and so that means it'll have 36 electrons when it's negatively charged with just 1 negative charge. So now we're looking for a 2+ ion that has the same number of electrons. So that 2+ ion we also said will have 36 electrons, but if it's a 2+ charge, how many protons is it going to have? 38. It'll have 2 extra protons and electrons to make it a 2+ charge. So that means this 2+ ion that we're looking for that has the same number of electrons will have 38 protons. And then if we go to the periodic table and find atomic number 38, which is here, they come in numerical order, so not hard to find, that's Sr, which is called strontium. You're responsible for knowing the first 36 symbols and what element they correspond to, but beyond that we don't expect you to know that, but you should at least be able to write the symbol because you can find it now, which is Sr2+. So strontium 2+ also has 36 electrons, but because it has 3 more protons, it would have a 2+ charge instead of a 1- charge. And then the last one here, which kind of gets at nuclear chemistry, not the nitty-gritty details, but an example of what happens in nuclear chemistry. So let's say we have a lead 2+ ion, and we lose 2 protons and 2 neutrons, also referred to as an alpha particle. Those alpha particles we talked about earlier is just a collection of 2 protons and 2 neutrons. Let's say that gets expelled from the nucleus. We lose it, and we want to know what is the new element that forms. So if we take protons out of the nucleus, we are going to change the element. That's the only way that can happen, and that's what we call nuclear chemistry, which we're not going to really deal with in this course. Well, let's assume we did it. So initially we need to find out how many protons, neutrons, and electrons this guy has. So if we go to the periodic table again and find Pb, it's down here in one of the last rows, and it's number 82. So lead Pb has 82 protons. It's helpful here to write it in explicitly because we're going to need that number as part of this problem. So initially we start with 82 protons, 125 neutrons. So again, that number is just taking the mass number, which is 207, and subtracting 82. So the sum of these, 82 plus 125, has to equal 207. And because it's a 2+ charge, it has 80 electrons. So that's the initial number of subatomic particles we have in the lead 2+ cation. That's exactly what we just sort of did above in a couple of other examples. Now we're looking for the new atom that forms when we lose an alpha particle. So we're losing 2 protons, so our new one's going to have 80 protons. It's going to have 2 fewer neutrons, so it's going to have 123 neutrons. And we didn't say anything about electrons, so we'll assume that it's going to still have 80 electrons. We didn't tell you that the number was changing. So our new atom is going to have these subatomic particles, and now we're just going to take these and rewrite the atomic symbol that results from that, which we also did before. So if we go to the periodic table, we have to figure out which element has 80 protons. So we find number 80 on the periodic table, which is the symbol Hg, which is mercury. Not intuitive, but that's what it is. That's mercury. So the symbol is Hg. The mass number, which we include in the symbol, is the sum of these two, the new number of protons and new number of neutrons, which is 80 plus 123, which is 203. That's our mass number A. And so we put that up here. And then the charge, we now have 80 protons and 80 electrons, so this new atom is not going to be charged at all because it has equal numbers of protons and electrons. So we stop there. We don't have to write a charge, and we don't have to write the 80, the atomic number down there if we don't want to. So that's a couple example problems. If those don't make sense, please get help from me and definitely practice them on the homework assignment this week.